So the sixth problem that we are going to discuss today, taking expansivity alpha and the compressibility beta, prove that number one, for a fluid, dou P by dou T at a constant volume is equal to alpha by beta. And number two, for an ideal gas, dou P by dou T at a constant volume is R by V. See, for any gas, any two of the three parameters can be used to define the system. They are called dependent and independent parameters. See, the pressure, volume, and the temperature, these are the three fundamental parameters which are to be defined to define the state of a gaseous system. But pressure and the volume, when any one of them is maintained constant, the other thing will change with the temperature. And also when temperature is maintained constant and the volume will change with the pressure and vice versa. Therefore, it can be easily said that volume is a function of temperature and pressure. Therefore, any two of these parameters can be given to define the state of any gas. But volume is a state function which depends upon only the initial and the final state according to thermodynamics. And the state function can be taken as an exact differential. That expression of the exact differential is this: dV is equal to dou V by dou T, that is a change of volume with a change of a temperature when pressure is maintained constant, into dt plus dou V by dou P at a constant temperature into dP. Let me say this is the equation number one. But alpha, that is the expansivity, is equal to 1 by V dou V by dou T at a constant pressure. And also the compressibility beta is equal to minus 1 by V dou V by dou P at a constant temperature. Here you have to understand one particular thing. The expansivity is done, or the expansion of the gas is done at a constant pressure. But compressibility is done, compression is done at a constant temperature, which is an isothermal process. Here it is isobaric process. Temperature is changed and the volume is changed by maintaining the pressure constant. Here the pressure is changed, hence the volume changes by maintaining the temperature constant, which is compressibility, and this is expansivity. Therefore, dou V by dou T at a constant P from this equation can be written as alpha into V. Similarly, dou V by dou P at a constant temperature can be written as minus beta into volume. So substituting the above values, so these values in the equation number one, we can write dV is equal to alpha V dt minus beta V dP. So at a constant volume condition, dV is equal to 0. As the dV is equal to 0 at a constant volume condition, we are taking the dV to be 0. Therefore, I can write alpha V dt minus beta VdP is equal to 0. When you take the volume as a common factor out, V into alpha dt minus beta dP is equal to 0. Volume change is 0, but volume cannot be 0. Hence, alpha dt minus beta dP is equal to 0, which means that alpha dt and beta dP are equal. So, when you bring dP by dt, which is equal to alpha by beta, this is the first proof. And for the second proof, in the previous problem itself, we have seen alpha is 1 by T and beta is 1 by P. Therefore, dou P by dou T at a constant volume is equal to 1 by T by 1 by P, which is equal to just the multiplication of the inverse of the denominator. It will be P by T. According to ideal gas equation, PV is equal to RT. So if you bring the T here and the V over there, P by T will be equal to R by V, which is the second thing we have to prove.